In the previous video on symmetry in general relativity, we had developed a formal way to describe how elements of a representation transform under an element of a group. So from here now, the next question then perhaps is, how can we build an invariant? Right? So now we want to figure out how do we build an invariant. Now, if one really thinks about it, it might seem that combining two objects which transform oppositely, transform oppositely, they would give you an invariant, right? So you take two objects and they transform in such a way that one transforms in an opposite manner as the other one, then it might seem that this thing would give you an invariant. Now, in fact, this is exactly what we shall do now, right? And so we will also take a cue from the familiar dot product, that is your vector u dot vector v. It gives you a number, right? So when you take a dot product of two vectors, it gives you a scalar or a number. Okay, so we are going to need help in this developing an invariant, and that would come from something that is known as the dual representation. Right. So say you have for any matrix representation R, this is your matrix representation, we can form a dual representation, and that would be represented as R tilde. This is a dual representation, right? So say if we form first of all, say that you have a transformation matrix A, and this transformation matrix belongs to some group G. Then what you can do is you can say that your R transforms as this transformation matrix acting on R, right? And likewise, your dual representation R tilde would transform as this thing. So this inverse of the transformation matrix transpose. So that is something you call a dagger in physics, or mostly in language of quantum mechanics. And then what you would have is R tilde, right? Now, if we can form this thing, that is R tilde transpose R, this thing would transform as A inverse. I'm writing this from these two things, right? So it would transform as A inverse transpose R tilde and the transpose of all of this times A R, right? So this R tilde transpose is this thing, and this R is this thing. So this is how they would transform, right? Okay, then if you look at it, this is simply equal to R tilde transpose A inverse transpose transpose, right? So we have transpose already here, and then we have this transpose over here as well, and times AR, right? Okay, so A is a symmetric matrix, right? And so this would be equal to R tilde transpose A inverse, right? This two transpose would sort of cancel each other out, and you have A R, right? Now recall that this thing is simply identity, right? That is because we said that A belongs to a group. A is a transformation that belongs to a group, and one of the properties of a group, if you remember, is A inverse composition A is an identity, right? And so this thing would then be equal to R tilde transpose R. Now, if you look at it, this thing is exactly the same as this thing. And what does that mean? That means that we have built ourselves an invariant that is R tilde transpose R is our invariant, right? Okay. Now note that I have simply over here just written down the dual representation and really did not tell you at all where does it actually come from. So then you could go ahead and ask me that if there is a systematic procedure to construct the dual representation R tilde, if you are given your representation R. So it actually turns out that for many cases, it can indeed be done provided a metric, right? So provided that you are given a metric, you can have a systematic procedure to construct the dual representation R tilde if you are given the representation R. So now I have talked about metric, and so let's go ahead and define a metric. So I'm going to actually even write this down here for you. So a metric G is a map from an element of a representation, say R, to a corresponding element of the dual representation, that is denoted with R tilde, right? Now what this means is that R tilde is given by G times R, right? And so then this G is actually a map. And now you have to note over here that G is always symmetric, right? Okay, it's a symmetric matrix. Now we are going to use this definition and see what does this R tilde transpose R being an invariant implies about the metric G. So this thing would have something to do with the metric G. Now we are going to use this definition and we are going to imply or implement it in this thing over here. So once we do that, what we have is R tilde transpose R is simply equal to, if you look at this thing, it is going to be G R transpose times R, and yeah, and this thing is then simply equal to R transpose G transpose R, which is equal to R transpose. Now note that we said that G is a symmetric matrix, then G transpose is simply equal to G, the matrix G, and we have this R, right? Now under a transformation matrix A, this would transform as A R transpose G A R, right? So this thing transforms as this thing over here under a transformation matrix A. So this thing is then equal to R transpose A transpose G A R. And this is for some A, that is the transformation matrix that belongs to a group G, right? And this thing can only be equal to R transpose G R if we have A transpose G A being equal to G, right? So this is the condition that we require, right? Now, the important lesson in all of this was that if we have some representation R of a group G, then forming a dual representation, that is R tilde, with the matrix G will give us an invariant, right? So that is to say that R tilde transpose R, you will get this if we have A transpose G A is equal to G. Again, for some A that belongs to the group G. Right. But you could even turn this around and you could say that given a representation R and a matrix that is G, we can use the condition, and the condition is A transpose GA is equal to G. We can use this condition and find the transformations that are A, which are going to leave R tilde transpose R as an invariant, right? So let me repeat this again, that we can say that given a representation R and a matrix G, we can use this condition over here to find the transformations that are A, that belong to the group G, which will leave this thing invariant, right? Now note over here that this statement is actually how we typically encounter symmetries in physics. That is, we start with stuff, and that stuff could be things like particles, fields, or any dynamical quantities for that matter, right? And etc. Now, all of which have some form of a representation. All of these form a representation, and then using the matrix G, we can find a set of transformations that are the symmetries of this invariant thing, that is R tilde transpose R. So from here you could say that given a group that is G, which is a set of these transformations lambda 1, lambda 2, lambda 3, and so on, and a linear representation R, that is simply means column vectors. What we can do is we can form a dual representation given these two, that is R tilde, such that R tilde transpose R is left an invariant. And we can do this using the matrix G that satisfies this thing, that is lambda I transpose G lambda I is equal to G, where these lambda i's are the transformation matrices. So this thing over here is the same as this condition over here, right? Okay, so we can do this, of course, for any lambda I that form a group, so that belongs to some group G. Okay, now we can work out this condition, lambda I transpose G, lambda I being equal to G. This can be actually worked out in two different ways, right? So, well, the first one, say that you are given a matrix. Uh, in fact, I'm sorry, you are not given a matrix. The first one would be that you are given some group G, right? So given a group G, which is a set of these lambda I matrices, right? If you're given this group, then you find the matrix G. The other way of working this thing out is that you are given a matrix G. So given a matrix G, what you do is you find transformations. Right? The transformations would be the group lambda I, right? So these lambda I transformations. Now, what we are going to do is we are going to start with an example of this, right? And then we will apply this thing over here to define special relativity. So we will use this part over here to define SR, right? Okay, so moving forward, let's actually go ahead and quickly look at rotations in 3 dimensions. So rotations in 3D, right? Okay, so here we focus on transformations of coordinates, right? And not on the transformations of the objects. And so what this is, it is known as passive rotations. Passive rotations. And in this, what we do is we focus on transformation of coordinates rather than the transformation of the objects. And this forms a compact, continuous, non-abelian group, right? And we are going to donate rotations with R. I don't think I had to say this, but anyway, right? R is going to donate our rotations. And so then what we can say is we could have a group, right, that is a set of rotations with angle theta, rotations with some angle phi, and rotations with some angle what should I call it? Let's just say psi, right? Let's represent another angle with psi. Now here these theta, phi, and psi are all continuous parameters, right? So what we can do now is explore their mathematical structure, right? And so we can do that by considering two objects in space. So we will take two objects in space. Also note that here we are exploring their mathematical structure, right? Okay. Right. Now, consider two objects in space and their positions are specified in a rectangular coordinate system. So we could specify the positions for, say, object A with XA, YA, and ZA, right? And for object B, we could have XB, YB, and ZB, right? Okay, so here we have a sense that if we know the distance between these two objects, then this should be actually an invariant under a change of coordinates. I mean, at least in this particularly simple case, right? Now, the distance between the 2 points in space is expressed as delta S is equal to the square root of XA minus XB squared plus Y. Let me just write this down again. Yeah, YA minus YB whole squared plus ZA minus ZB whole squared. So hopefully you know this formula for distance, right? Sorry, I just erased the square root, right? My bad. Okay, so this just comes from simple coordinate geometry, right? That you do in your high school mathematics, perhaps. Okay, so over here, this thing can be labeled as some delta x. This thing could be labeled as delta y, and this thing would be labeled as some delta z. And then in the shorthand notation, your distance formula simply becomes delta x squared plus delta y squared plus delta z squared square root, right? Okay, now here comes the interesting part. What we are going to do is we are going to deconstruct this formula, right? And for that, you should consider that delta S squared is expressed as the row matrix delta X, delta Y, delta Z times this column matrix delta X, delta Y, delta Z, right? So if you take this product of these two matrices, you end up back in this way, right? So what we are doing is, again, we're deconstructing this thing. Now, we know that if we change to a new related coordinate system, then all of these, say for, let's look at object A. So these coordinates that are x, a, sorry, not x, here I would have y. So xa, ya, za, they all transform in the new coordinate system as some x prime a, y prime a, and z prime a, right? And so what this does is this simply implies that delta x, delta y, and delta z would transform as delta x prime, delta y prime, delta z prime, right? And these will change, right? These things, these coordinates would change for transformation to a new coordinate system. What will not change is this delta s squared, right? So this has to be invariant, which is the distance between the two objects, right? Of course, the distance between the two objects in a simple case, which we are studying over here, it will remain invariant, right? Okay, so before I proceed further from here, let me just tell you that what we are doing is we are going to see that YG is called the matrix, right? And we are going to understand the matrix in a, you could say in depth, right? Okay, so from here now, if our rotation is represented by a linear operator, right, then we can have this column matrix delta x, delta y, delta z transforms as delta x prime, delta y prime, delta z prime, right? And which is actually equal to some rotation operator, right? Which is the linear operator times delta x, delta y, delta z. Now, this actually implies that your row matrix, that is delta x, delta y, delta z, that transforms as delta x prime, delta y prime, and delta z prime, right? Which is actually equal to, if you were to apply a rotation operator on the column matrix, that is delta x, delta y, delta z, and you were to take the transpose of this thing. So what a transpose does is it converts your column matrices into row matrices. So that is what this thing would be equal to, right? So actually let me write it over here. Delta x prime, delta y prime, delta z prime, which this thing over here is your row matrix. And this thing over here is your column matrix. And that is why we had to take this transpose, right? So this is transpose. I know I did not need to tell you that, but anyway, right? Okay, so from here then what we could say is that delta s squared is equal to this row matrix delta x, delta y, delta z times the column matrix delta x, delta y, delta z. This is it transforms as, right, or is equal to delta x prime, delta y prime, delta z prime times delta x prime, delta y prime, delta z prime. And note that I use this equal to sign because this thing over here has to be invariant, right? So we are just using this condition, and now what we will see is that this thing over here is simply equal to delta x, delta y, delta z times this r transpose r, which again note that this is the this is a linear operator. R is a linear operator, and times delta x, delta y, delta z, right? Now from all of this, what we arrive at is that we have an invariant, that is a delta s squared, and this thing delta s squared actually requires something. And what is that? That is that this thing over here, r transpose r, what does that have to be, right? If you look at this thing and compare it with this thing, it has to be 1, right? Or the identity. So this is the condition that is required, right, for the delta s squared, this thing. Now from all of this, let's actually go back and compare this thing with what we were starting off with, that was lambda transpose G, lambda being equal to G. Now here what we see is that in the case of 3D rotations in Euclidean space, what does G has to be? It is identity, right? And that is simply the matrix 1 0 0 0 1 0 0 0 1 in 3 dimensions, right? Okay, so now we should understand the distance expression as let me write this down over here, and in the next video I will use a smaller font, right? Okay, so yeah, we should understand the distance expression as delta s squared is equal to delta x delta y delta z row matrix times this G that we have, the matrix in 3D space, that is given as this identity, a 3 cross 3 identity, and times delta x, delta y, delta z. Now, don't worry if you are kind of confused over here. I'm going to actually give you an example which would make all of this very clear to you, right? But at least now I hope that you can understand why we called G a matrix in the first place, right? Now, for space-time transformations, it actually plays a crucial role in defining distances, right? That's what matrix does for space-time transformations. In fact, it will actually tremendously help us to think of coordinates as labels that are distinguishing points in space-time with no intrinsic notion of distance at all. So we just think of them as labels that are differentiating between the 2 points in space-time, 2 or more points, right? Now, what we do is we will actually encode the distance in our metric itself. So now, to make all of this even more concrete for you, or let me just say that to give you an example, consider a two-dimensional case where you have polar coordinates, right? And the coordinates are r and theta. Then infinitesimally, you would have ds squared being equal to dr squared plus, now if you remember this, that is r squared d theta squared, right? And so what is that? That in matrix form, that could be written as this row matrix dr d theta times this transformation matrix, that would be 1 0 0 r squared times the column matrix dr d theta, right? And this thing, with the help of the matrix, it gives you this distance formula, that is ds squared is equal to dr squared plus r squared d theta, right? Now here, note that if you had only tried to use the coordinate differences, right? So the coordinate differences, what you might have written in that case would be something like, you would have just wrote ds squared equal to dr squared plus d theta squared, right? Exactly, because you would have not considered the matrix, you would have just considered the coordinate differences, that's all. And you would write this thing over here, which is absolutely wrong, right? It's wrong. The correct formula infinitesimally is this one with the help of the matrix that we construct. Now, this lecture is over here. In the next one, what we will do is we will state the premise of the special relativity, and we will see what these lambdas that I've been talking about really are. And with those, what we will arrive at, I should say, we would beautifully arrive at the velocity addition formula in special relativity, right? And then we would look at even things even more interesting, and finally we would come to the point that we would talk about vectors and dual vectors, and then we would define tensors and all of these preliminary things for general relativity. We would talk about manifolds, and we would see how these manifolds are related with this metric. And that's when we will, after that all, we are going to arrive at Einstein's field equations, and things would start getting even more interesting from there.